Good morning everyone. Today my topic is about surface charge density measurement. I am Jinaresh from ECE second year. This is a PPT of AMDL subject. Let's get into the topic. Surface charge density sigma is the quantity of charge per unit area measured in coulombs per square meter at any point on the surface charge distribution on a two-dimensional surfaces. Assume that the surface that is being tested is of infinite extent and has a uniform surface density, charge density sigma. Figure represents a simple diagram showing a circular field meter sensor over the measured surface. A surface area A seen by the sensor can be approximated by the following equation. So from this figure we can the surface area is the sensor can be approximated by the equation A is equals to pi into d plus 2h by 2. From the Gauss law, when we apply Gauss law, the dependence between the electric field E detected by the field meter and surface charge density R can be easily calculated as E is equals to the electric field intensity E is equals to sigma by 2 epsilon naught. The reasonable approximation of charge Q on the surface can be calculated from the field meter readings. So from this diagram we can write the Q charge value is equals to 2 into E into epsilon naught A, and where Q is the charge and E is the electric field intensity and epsilon naught is the permittivity of free space and A is the area. The above equation can be written as where Q by A equals to sigma, so that sigma is equals to 2 into E into epsilon naught. This is the figure 1 which shows the surface area detected by the field meter. This is the surface under the test and the distance d is shown in the figure. In the particular case, with all the assumptions in place, the field E does not depend on the distance from the plane. In practice, we deal with finite surfaces and field E is affected by the surrounding object, the field meter itself, and the operator who holds the field meter. Consider another case where the surface that is being measured in the finite extent in a form of a disk of radius r and a uniform charge density r. Again, such uniform charge distribution can be found on the conducting metal surfaces except for the surface edges. Theoretically, from the Gauss law, the electric field can be written as E is equals to sigma by 2 epsilon naught minus sigma into h by 2 epsilon naught under root r square plus h square, and it is a measure surface charge is Q is equals to the surface charge Q is equals to 2 into epsilon naught E. So from this, when 2 epsilon naught goes to this side, then sigma is equals to 2 epsilon naught into E. So the 2 epsilon naught into E is into A by 1 minus h by r under root r square plus h square. The geometry dependence portion of the electric field vanishes as the ratio of r by h grows larger. This shows the figure. When r by h grows larger, then the electric field vanishes. It is important to understand that the presence of the field meter sensors will disturb the electric field distribution. A more common situation is when the charged surface is additionally coupled to the earth ground at the location other than the backing plane, which is a usual case of surface charge measurement configuration. The field intensity detected by the field meter would be determined by the equation E is equals to sigma into h by epsilon naught into d plus epsilon d into h dash, where d is the thickness of the dielectric distance and ed is the dielectric permittivity of dielectric material. If distance h is much greater than the thickness d, we can written as E is equals to epsilon sigma into d by epsilon d into h. that is equals to sigma into pi into r square by c into h. Click to add the disk with the radius r. C1 is introduced with the equation as geometrical capacitance of disk with respect to the backing ground plane. The C1 capacitance C1 is equals to epsilon is equals to d pi r square by d. Surface charge distribution measurement. An ESVM measures the evolution of surface charge measurement, the potential difference between the at ground and an object under test. Unlike in field meters, the ground reference point is not present in the close proximity of the voltmeter sensors. At an ESVM measures the voltage that is applied on the voltmeter sensor. So the ESVM circuit measures the voltage of the voltmeter sensors. When the uniformly charged plane is of the finite size, the disk with radius r, V is equals to sigma by 2 epsilon naught into under root of r square plus h square minus h minus r, where h is the distance between the disk and the grounded reference plane. For the finite value, r is very much greater than h. V is equals to sigma into, so this entire equation can be written as a simple h, so that V is equals to sigma into h by 2 epsilon naught. The ESVM reading will be dependent on the capacitive coupling of the distributed charge of the surrounding object on coupling of the ESVM sensors to be measured surface. The figure below shows the electric potential distribution of the finite plane with the non-uniform surface charge distribution. To do any meaningful measurement in this condition, all the capacitance interactions should be well defined, with a very difficult to obtain in practice. The ESVM sensor and the body of the probe are driven to the potential of the measured surface. So this figure shows the electric field lines where influences the ESVM of the surface charge measurement model. The calculations of the surface charge becomes very simple, although it should be considered as the approximation. Q is equals to C1 into V, and the DC feedback ESVM allows for very slow proximity of the sensor to measure the object. This capability makes it possible to do a very precise charge distribution mapping. Conclusion: electric potential measurements are affected by the geometry of the measurement setup, but to a much lesser degree than field meter or AC ESVM measurement results. In fact, the DC ESVM was the only instrument which is an experiment that allowed for accurate computation of the surface charge density. It is important to consider the size of the surface that is being measured and the distance between the sensor of the surface. The ESVM allows for precise measurement of charge distribution when charge is coupled to well-defined electric potential reference point. Otherwise, the measurement can be difficult. Thank you.